All right, reaction yield or percent yield. All right, in a perfect world, you would always get 100% yield. All right, let me repeat that. In a perfect world, you would get 100% yield. If you did a reaction and you would expect 10 grams, like the previous problems we did, you would, in a perfect world, you would isolate 10 grams. Okay. However, we don't live in a perfect world. So there's many reasons why we rarely actually isolate 100%. It could be because our technique, we dropped a little bit of it, or we didn't actually perfectly isolate every single morsel of atoms. All right. Or the reaction just does not go to completion. There's sometimes reactions don't go to completion for whatever reason. They only go to maybe 50% completion, so we only isolate a portion of that 50%. Okay, so what this calculation does is it actually tells you what percentage of the product you actually isolated based on your calculations. Okay, so you have an actual yield and a theoretical. The theoretical yield is what we have just been doing in all these problems. All right, in theory, based on the calculations, I should isolate, oh, I erased it. I should isolate X amount of my product. Okay, but actually, when I did the experiment, I only got this amount. So I can figure out what percent of the theoretical amount I actually determined. Okay, so it says in practice, the actual yield is the amount of product actually obtained from a reaction. And remember, it's always less than the theoretical yield. This number is always going to be smaller. And I hope for those math people, you're like, oh yeah, of course, because a percentage can never be greater than 100%, right? We just told you, I told you about the conservation of mass. I cannot produce more than what I react. If I have 50 grams of reactants, I can't magically make 60 grams of reactants. I always have to make another 50, okay? So, and the theoretical is what you do on paper, okay? So we're actually going to do a full problem. This is actually aspirin, an aspirin example. And then we're going to do a percent yield. So notice, in a certain aspirin synthesis, 104.8 grams of salicylic acid, this is salicylic acid right here, is reacted with 77.47 grams of acetic anhydride. Calculate the percent yield of the reaction if 105.6 grams is isolated, okay, or produce. So in your mind, you should be saying, hey, I have two masses for my starting material, so this looks like a limiting reagent problem. I got to figure out which one's my limiting reagent. Based on that, how much of my final product is going to be produced, okay? And based on your final product, you have to compare that number with the amount of compound that you actually isolated, okay? So that is what we're going to do. Okay, so I have 104.8 grams of my acetylsalicylic acid. I'm sorry, of my, that was pretty impressive, wasn't it? My salic acid. This is salic acid. This is acetic anhydride. And then this is my aspirin. I'll just call it ASP. Okay, I'll use these as abbreviations so I don't have to write so much down here. So 104.8 grams of my salic acid, used a molecular weight of salic acid, which is 138 looks like 1 grams is to 1 mole of my salic acid. This is a 1-to-1 ratio, so 1 mole of salic acid is to 1 mole of aspirin, because we're trying to figure this out. Okay, times the molecular weight of aspirin, which is 180.2 grams, is to 1 mole of aspirin. So this equals 135.7 grams of aspirin. Now, if you like to put this on pause and now figure out how many grams of acetic anhydride it's going to take, you can come back and compare your results with mine. So put it on pause now. Okay, welcome back. So I'm going to do it. You're going to start with 77.47 grams of acetic anhydride. The molecular weight of acetic anhydride, I get approximately 102.1 grams. It is also a 1-to-1 conversion, or mole to mole. 1 mole of AN is on the bottom. This is 1 mole of ASP, aspirin, which is acetylsalicylic acid. Say that 10 times fast. I know some of you are doing it right now, which is kind of funny. Anyways, that gives you 136.7 grams of aspirin. So what's my limiting reagent? It is the salicylic acid because this number is lower. Okay, so you're putting in a little bit extra of the acetic anhydride just to make sure that you consume all your salicylic acid. Okay, so 135.7. Now the question is that my actual or is that my theoretical? This 135.7. That is my theoretical. My actual is this 105.6. That's my actual. So what percent yield? If this is how much I actually got from the equation, you take that, divide it by how much you calculated, times 100, and you get 77.8%. That means you isolated 77.8% of how much you should have gotten from the equation. That means your, whatever, was it 22.2 percentage of it got lost somewhere. Maybe you dropped it in the workup, maybe the reaction didn't go to completion. Maybe your balance wasn't working and you thought you did 136, but actually is 126. Maybe you had, a helper and they only weighed out 125. There's so many variables as to why it didn't go to completion. Okay, but that is basically how you do percent yields. Okay, hopefully you're kind of seeing it, that you're understanding this. Okay, aqueous reactions. Aqueous reactions. Here's just a problem. I'm not going to write anymore. I'm just going to kind of go through this. But basically, this is where you use molarity rather than mass. All the examples we've used were always grams per mole, and we're starting with masses, grams. But you don't have to. You can start with molarity. Remember, molarity is moles per liter, and you're starting with a certain quantity, okay? And you still have a balanced equation. So determine how much of a 0.25 molar solution, all right, of silver nitrate is necessary to precipitate all the chloride in 2 liters of water in which the chloride ion concentration is 0.0173 molarity. Okay, so my chloride concentration is this. Okay, the chloride volume is 2 mils, and I got to figure out the volume of my silver nitrate or our silver amount. All right, and then there's a part 2. So how they do it is you start with your 2 liters, that's your volume, and your molarity of your chloride ion, which is 0.0173. So let's go back. Okay, so you start with your 2 liters, because that's what you're starting with. Your molarity is 0.0173 moles per liter. All right, this is of the is this the chloride ion concentration. Okay, because remember, what are you trying to get to? Moles. Now you have to convert moles of chlorine to moles of silver. Well, there's 1 mole of chloride ion to 1 mole of silver ion. I get that from the balanced equation. All right, so, and then I have this, remember this is moles per liter. So 0.250 moles of silver is to 1 liter. So this is my problem. 2 times 0.0173 times 1 times 1 divided by 2.50, and you should get the volume of how much of the silver ion you should have. So let me quickly do that, and you should get your volume in liters is 0.1384 liters. Let's see how many sig figs. Looks like 3 sig figs. So let's put this in milliliters. 1, 2, 3. So 138 milliliters. So you've just calculated the volume of your 0.25 molar solution. Okay, and you can see right there, 0.138 liters. Okay, so they took the volume, they took the molarity. This was the molarity of the chloride ion. They found the moles of chlorine, 1-to-1 conversion to get the moles of silver. Now, they're stopping after each equation. You can do that if you want. I like to do it all at once. And then they use the molarity. The next problem is determine how much of the 0.250 silver nitrate is necessary to precipitate all the chloride ion in a barium chloride solution. Barium chloride, BaCl2. Notice it's a 2-to-1 ratio. So why don't you go ahead and see if you can practice this on your own, and when you come back, you can look at the answer. Okay, so welcome back. If you didn't do it, do it. All right, So here's the equation. Again, 2 liters with that molarity. It's a 1-to-1. I'm sorry, that's part A. Here's part B. 1.5 liters of barium chloride. There's the molarity. This time it's a 2-to-1 solution. For every 1 mole of barium chloride, you have 2 moles of chlorine. And then you're also using, for 1 mole of chlorine, there's 1 mole of silver. This is kind of a more complicated one. All right. And then you're multiplying it by 1 divided by the molarity of silver, and you should get 0.522 liters of silver. All right, like I said, I will post practice problems, or we'll do them in class. Okay, let's end this video, and then we can come back with 10.5 on the next video.